In this lesson, we're going to be solving linear inequalities. So let's look at this looks like. We have an equation here, and instead of an equal sign, which we are used to seeing, remember our y equals mx plus b. This is the equation of a line in slope-intercept form. We have the same thing, but this time instead of an equal sign, we're going to have an inequality sign. So first, we're going to graph it the same way, where we graph. First, we have to write it in slope-intercept form, but this one already is in slope-intercept form. Now we can graph by using the y-intercept and the slope. Remember, we always start with the y-intercept. The y-intercept is 4, so here's 4 on the y-intercept. Then the slope is 3, which should be 3, a rise of 3 and a run of 1. So we go up 3, 1, 2, 3, over 1. There's another point. We could do it again, up 3 over 1. Okay, so we've discovered where the line should be. Now, before you draw the line is either going to be a solid line or it is going to be a dashed line. That is based on this sign right here. If it is less than but not equal to, it would be equal to if we added this underneath it. If it's less than or greater than but does not have equal to, it is a dashed line. When we were graphing inequalities, we would have done that with a circle dot, without a filled-in dot. The way we represent that on a graph like this is with a dashed line. If it is less than and equal to, or greater than or equal to, then we do the solid line. This one's dashed, this one's solid. It's the difference between our circle dot and our filled-in dot. So since this one is less than but not equal to, it is a dashed line. It'd be like a circle dot. Now you are not finished. This is the most important thing. You are not finished until you're going to shade one side, because we are saying that the solution is less than this line. That means it's either on the right side or the left side of the line. Either all of this side is a solution or all of this side is a solution. So you have to look at and discover which one it is. Oops, that's funky. So since this is less than, we're always going to be on the bottom of the line. So look at the way the line is positioned. What looks like it would be beneath it? It looks like this side would be beneath it, but we can check it. So we're going to pick a point. If you can pick 0, 0, it's a really easy one to pick. At that origin, x is 0 and y is 0. Let's plug them back into this equation. So let's plug in 0 for y, and we're going to plug in 0 for x and see if this is a true statement. 0 is less than 4. Is 0 less than 4? It is. That checks. So that means that this point is a part of the solution, and that is the correct side to shade. Less than is always going to be below the slant. Okay, so let's try it again. This equation is not in slope-intercept form, so the first thing we want to do is put it into slope-intercept form. Remember that is y equals mx plus b, where you have the y term on the left side, and on the right side you have the x term and then the constant. Well, looking at this equation, the 3x, the x term is not on the right side. It's going to come over here, and it's a bully, and it tells the 6 to scoot over. You're in my place in line. When we do that, the 2y is still on the left side. When the 3x is moved to the other side, we have to use inverse operations. So it becomes a negative 3x, and he tells the 6 to scoot over. Now we're not finished until we get y by itself, and y is being multiplied by 2, so we want to divide all 3 parts by 2. And when we do that, we get the equation in slope-intercept form. Whoops. And that would be y is greater than or equal to a negative 3 halves x plus 3. Now we can easily graph it by using the y-intercept and the slope. Remember, we always start with the y-intercept. So we go on the y-axis and we put a 3. The slope is negative 3 halves. So I can go down 3 to the right 2, down 3 to the right 2, and so forth. So now we know where our line is going to be. We have to decide, is this going to be a dashed line or a solid line? Notice that this is equal to right here, so that means we're going to have a solid line. So, and then it says that it's greater than. So here's our line, somewhere around there. Greater than would be above the slant. Since this is a negative slope, this would be below the slant. This would be above the slant. And when it's greater than, you want it to be above the slant. If you're not sure, you can check a point. Remember how simple it was to check the point 0, 0? We see the origin right here is not a part of the solution. So what happens if we plug in 0, 0? 0 is greater than or equal to. If we plug in 0 to this term, it goes away. Is 0 greater than 3? Well, it's not. So that's not a part of the solution. And that's good because the solution we decided would be over here above it. That means all of these ordered pairs could be a solution. Not just one, but the entire shaded area. Here's another example. Again, it is not in slope-intercept form. So we have to move the x term to the other side. When we do that, we use our inverse operations. So it's going to become a negative 4x. So that gives us negative 3y is greater than negative 4x, and he tells the 12 to scoot over. Now we divide all three parts by a negative 3, and our equation would be y is greater than, oh, looky here. Notice we are dividing by a negative number. Remember our rule about dividing by a negative number. Right here we were dividing by a negative 3. We have to flip the sign. And that would be 4/3 x minus 3. We're ready to graph by starting with our y-intercept of negative 4. So we go to negative 4. Our slope is 4, a rise of 4, and a run of 3. So we go up 4 over 3, up 4 over 3, 1, 2, 3. We can see where our line's supposed to be. Now, is it dashed or solid? It is not equal to, so we're going to be doing a dashed line. Now the solution is going to be one side or the other. We are not finished until we shade. We flipped the sign, so y is less than. That means it's going to be below the line, below the slanted line. This looks like to me that it's below, but again, we could check our point 0, 0. Is 0, 0? We don't want 0 to 0 to be a part of the solution, so we plug in 0. This term goes away. Is 0 less than negative 4? No, it is not. So that's good that it's not part of the solution. That means the part of the solution is everything in the shaded area. You are not finished until you shade. Now we were talking about how you can check to make sure a point is actually part of the solution. Tell whether the ordered pair is a solution for the inequality. All you have to do is plug in the numbers and see if it is a true statement. So with the ordered pair 7, 3, which is right here, once we graph it and we shade it, would that be part of the shaded area? Well, we don't have to graph it and shade it to figure that out. All we have to do is plug this 7 in for x and the 3 in for y and see if it is a true statement. So instead of y, we're going to write 3 is less than. In place of x, we're going to write 7 minus 1. Is this a true statement? Is 3 less than 6? Well, 3 is less than 6, so yes. If we graphed that, it would be part of the solution. This is what it looks like graphed, and this is what it looks like shaded, and look, indeed it is part of the solution. But we could figure that out without actually graphing it. Let's try that again. Would the ordered pair 4, 5, which is located right here, be part of the solution, part of the shaded area from this equation? So let's plug in 4 for x and 5 for y. That would be 5 is greater than 3 times 4 plus 2. 5 is greater than 12 plus 2. 5 is greater than 14. Is 5 greater than 14? It is not. That means it's not. So we don't want that to be in the shaded area. So look what happens if we graph it. Here's what it is graphed. Here's what it is shaded. So indeed that was not part of the solution. Now you need to be able to look at a graph and be able to write an inequality for that graph. So we can do this by finding first we need two things. We need the y-intercept and we need the slope. Where does it cross the y-axis? It crosses at a positive 2. So we know at the end of the equation we're going to have a positive 2 for the y-intercept. For the slope, we need to find another place where it crosses at a good intersection. I think it looks like it crosses here pretty good. I'm not sure if it crosses there good or not. This graph is not very clear. Let me see if I identified some good points. This is the good point. Your graphs will be a little clearer than that. And most of the time we even put points on them to help you out. But you want to find a place where it crosses at an intersection. And this graph was hard to see where the intersections were, but there they are. So from the y-intercept, we went up 2 and to the right 1. That would give us a slope of 2 over 1. So there's our slope of 2 over 1, but the 1 doesn't have to be there. Now, it's graphed below the line, so we know it's less than, and we know it's equal to because it is a solid line. So we found the y-intercept, found the slope, looked at the line to see if it's going to be dashed or solid, and then is it below the line or above the line? These are all things that we have to look for. Okay, so let's try again. First we start with the y-intercept. The y-intercept is negative 2, so that's our y-intercept. For a slope, it looks like right here and right here, they're good intersection, good points. So it's up 2 over 2. That would be a slope of 2 over 2, which is just a slope of 1. So that would just, the 1 can be invisible, so we'll just call that x. We notice it's a dashed line, but that it's above the line, so that's going to be greater than, but not equal to, x minus 2. So that's the thought process you have to go through when writing the equation. Start with the y-intercept. You kind of start at the end and work your way this way. Start with the y-intercept, figure out the slope, look to see if it's dashed or solid, and if it's above the line or below the line. Let's try it again. Remember, we start with the y-intercept, which is right here, which is 4. That's going to be at the end. Find another good intersection that looks like right here and right here. So we go down 2 to the right 1. Down 2 to the right 1 would be a slope of negative 2. So our slope is negative 2x. It is, we know why. It is a dashed line, so we know it's not equal to, and it's above it. So we're going to say greater than. If you're not sure about the sign, you could test a point, okay? So I could pick a point. Let's pick 0, 0. We don't want 0, 0 to be part of the solution. So 0 is greater than 0 plus 4. Is 0 greater than 4? It is not, so we did not want 0, 0 to be part of the solution. So I know that I have the correct sign. Okay, let's look at this. Clark is having a party at his house. His father has allowed him to spend at most $20 on snack food. So his dad gave him a $20 bill and says, knock yourself out, can't go over this. He would like to buy chips that cost $4 a bag and pretzels that cost $2 per bag. So the question is how many combinations of chips and pretzels can he buy and how many of each? So first we're going to write this like we were modeling with expressions in our last lesson. This time it's just with inequalities. So again, we have pretzels and chips. Neither one of them is really dependent on the other. So since they mentioned chips first, I put that on the x-axis. And pretzels they mentioned second, so I put that on the y-axis. What would our equation be? $4 for chips. That's 4 times the number of chips. And $2 for pretzels, so that's 2 times the number of pretzels, at most $20. So $20 is the most he can spend, so that's the greatest he can spend. Or he could spend exactly $20, so it could be equal to as well. Now we can graph it by finding the x and y intercept. Remember, to find the x-intercept, we plug in 0 for y. That would just give us 4x is less than or equal to 20. So x is less than or equal to 5. So he could buy 5 or less bags of chips. 5 or less bags of chips. And to figure out the number of pretzels, if we plug in 0 to x, we would have 2y is less than or equal to 20. So he could buy 10 or less bags of pretzels. Now we can graph that. We notice that it's equal to, so that would be a solid line. Now everything, since it's less than, is below the line. That means any ordered pair in this shaded area are combinations of chips and pretzels that he could buy. He could buy 2 chips and 0 pretzels. He could buy 2 chips and 4 bags of pretzels. He could buy 3 chips and 1 bag of pretzels. That's the ordered pair 3, 1. For the ordered pair 2, 5, that would be 2 bags of chips and 5 bags of pretzels. So these are all the combinations of numbers of bags of chips and pretzels that he can buy and spend less than or equal to $20. There's the PowerPoint quote. There it is. So you can just pick one, and then if your assignment said, let's see, usually it says give 2 possible combinations. So what you would do down is just pick a couple of points in here. I might want to pick that one and that one. So I would say that that is 3 bags of chips and 1 pretzel for that order pair. And for this order pair, that would be 1 bag of chips and 4 pretzels. And you could do that with every one of these ordered pairs. But you only have to do 2. So pick 2 points. Good luck.